Sir, how to identify which hybridization will take place? Means D2, sp3, sp3, D2. Among these, which will take place? How should we identify that? If we are given one compound name.
Okay, I have classified the ligands into three categories, isn't it? Sigma donor,
Yes.
sigma donor, pi donor,
Yes.
and pi accept sigma donor, pi acceptor ligands.
Yes.
Sigma donor and sigma donor, pi donor ligand. In general, they are weak field ligands. That means the metal ligand interaction is not very strong. Whereas pi acceptor ligands, they are strong field ligands. That means the metal ligand interaction is strong. As a result, they can provide the pairing energy. So if I give you an example, say cobalt. These are the two same metal, same oxidation state of the metal, cobalt. In one case, the fluoride as a ligand. Another case, the cyanide as a ligand.
Yes.
Fluoride is a comes under sigma donor, pi donor category. Cyanide is a pi acceptor ligand. Okay?
Yes.
Now, cobalt 3 has D6 configuration because cobalt is D7H2, so cobalt 3 is D6. Now, when the ligand is a weak field ligand, where the interaction is not very strong, then the pairing energy will not be provided. So there will be 4 unpaired electrons. Is it clear?
Yes.
The fluoride is a weak field ligand, so it cannot provide you the pairing energy. So the Hund's rule will be followed. That is, all orbitals will be singly occupied before pairing of electrons, where the ligand is a weak field ligand. In this case, you don't have any vacant d orbital, so in this case it will be sp3d. Because there is no d orbital available. I need a vacant d orbital to accept a pair of electrons from fluoride atom. But in this case, cyanide is a strong field ligand, so it can provide the pairing energy. So all 6 electrons will be paired in 3 orbitals. Now I have vacant 2 d orbitals. So in this case it will be d2sp3. So whether you have the vacant penultimate d orbital available or not, that depends upon electronic configuration of the metal, the nature of the ligand, if it's a weak field ligand or a strong field ligand. Okay, we will discuss this in more detail. Don't worry about it.
Yes.
Any other question?
Sir, in that polymerization of ethene with Ziegler-Natta catalyst, sir, I read that they means there is a bond formation between that Ziegler-Natta catalyst and ethene, and the long chain is formed. Sir, how then it is separated?
After some time, they add acid to they cleave the aluminium carbon complex. So, hydrogenation also will do that. If you pass hydrogen, it will cleave the aluminium carbon. and it will form the aluminum hydride and the alkene. Okay, now is there anything to?
Yes, sir. That C2O4 minus oxalate ion is a didentate ion, but still there are 4 oxygens, so all 4 should donate lone pair. I only
One is a keto, another is a enolate oxygen. So the O minus is a better electron donor than the neutral oxygen. Do you agree with me?
yes,
If you have O minus, that means that you have an additional electron on oxygen. And in the other case, there is no negative charge. Which will be a better donor of electron? The one which has a negative charge. That is why it will only 2 oxygen donors will function as a ligand and not all 4.
So, but in other cases, when oxygen is attached to nitrogen in NO2 minus, then nitrogen and O minus both are ligands, means both donate the lone pair. So in that case,
Not at
N
the
also
same-
donates.
Not at the same time. They are called ambidentate ligands. I have not discussed this. Okay,
Yes,
you are asking something, skipping. Everything will come.
yes,
Ambidentate ligands are the ligands which have more than one donor atoms in a molecule, but only one atom at a time forms a coordinate. That is the distinction between an ambidentate ligand and a bidentate ligand. All ligands do not function as ambidentate ligands.
Sir, in the last lecture you discussed about charge transfer transition. Sir, I'm not getting how is charge transfer transition related to color of that ions. Some compounds you told like Cu2O and KMnO4.
I want to see your face. I cannot see, Yes.
So you give examples of Cu2O, KMnO4, Ag2S3 and all. So you said that they don't possess d orbital or their electronic configuration is d0. Still they exhibit colors due to charge transfer.
D0 or D10?
D0 or D10. So you said that they exhibit colors due to charge transfer transition.
Because
So I'm
that-
not getting how is.
Because there is no D-transition is not possible.
Yes.
When you don't have a d electron, how DD transition is possible? And when you have DT in your configuration, how DD transition is possible? So an electron is transferred from one atom to the another, and this transfer requires part of the energy of the visible light. As a result, they should sodium chloride. In sodium chloride, the chlorine will transfer an electron to sodium. But that requires ultraviolet energy. So it is not colored. So it is how much energy is required to transfer the electron from one atom to the donor to the acceptor atom. If it falls in the part of the energy of the visible light, then the remaining part is transmitted and that gives the color.
Yes.
Okay. Is it over?
Yes.
Is there any question? Okay. So write down that sigma donor and pi donor ligands, sigma donor and pi donor ligands are normally weak field ligands and they stabilize the metal in a high oxidation state. So metal, when it is in a high oxidation state, The sigma donor and sigma and pi donor type of ligands can stabilize the metal in high oxidation state, because metal in high oxidation states are electron deficient. And since these ligands are electron donors, so the deficiency of the metal is neutralized. As a result, they stabilize the metal in high oxidation state. And normally they are weak field ligands. They will not provide the pairing energy. Normally, up to, I will tell you now why. Whereas pi acceptor ligands will stabilize the metal in low oxidation state. And they are the strong field ligands always. There is no normal. Always they are a strong field ligand. They provide the pairing energy to pair the metal electrons. They provide the pairing energy to pair the electrons of the metal ion. Okay?
Yes.
Now, why I said that, normally, because up to iron 3, halide ion, water, hydroxide ion, ammonia, they are weak field ligands. Up to iron 3 plus, remember, if the metal oxidation state of the metal is less than 3, like nickel 2 plus, cobalt 2 plus, then all these will be weak field ligand. But for cobalt 3, except this, all are strong field ligand. They provide the pairing energy. That is why I said normally they are weak field ligands. Why normally? Because up to iron 3, they are weak field ligands. But right of ferric, all metals in class 3 oxidation state, these ligands will behave as a strong field ligand, except the halide ion. For cobalt 3 complex, except except these two, all other complexes of cobalt 3 are low spin. That means they don't have any unpaired electrons. They are diamond metals. because all 6 electrons have been provided pairing energy, so they paired in 3 orbitals. In this case, it will be D2sp3. In this case, it will be sp3d. Is it clear to you now? So it depends on the nature of the metal, it depends on the nature of the ligand, okay? And it also depends upon the geometry. Octahedral can show high speed, low speed, but tetrahedral will always show high speed. That means pairing is not possible. Now, if you have 6 electrons and 5 orbitals, 6 electrons have to be paired. If I have 5 orbitals and if I have 6 electrons, the 6th electron has to be paired with one of the 5 electrons. That is not a pairing. That is not a pairing energy. Pairing energy means when all the electrons are paired. Now, unless you have odd number of electrons, like D5. Ferric. In this case, you see, water is a weak field ligand up to iron 3. Iron 3 is D5. So you have iron 3 is D5 and D5 will be all, in this case, for water as a ligand, the distribution of electron will be 1, 1, 1, 1, 1. So there will be 5 unpaired electrons. Whereas, in this case, there will be only 1 unpaired electron. Because if you have an odd number of electrons, can you pair all of them? You can't pair. So there will be odd electron, but all other electrons are paired. So how do I differentiate that whether the pairing has taken place or not? By measuring the magnetic moment. This one will have the mu spin is root over n into h plus 2, 1.73 Bohr magneton.
Yes.
Whereas here, it will be root 35 Bohr magneton.
Yes, sir.
So by measuring the magnetic moment, I can differentiate what type of ligand is, whether the metal-ligand interaction is strong or not, whether the pairing energy has been provided or not, all, and what type of hybridization it will have. In this case, I told you it will have sp3d2.
sp3d.
In this case, you will have d2sp3 because you have 2 d orbitals available.
Yes.
Is it clear to you now that you asked me whether it is d2sp3 or sp3d2? Now, there is a limitation, okay? Now I will come to that. When you use the d orbital before s, then you call inner orbital complex.
Yes.
And when you use outer d orbital, that means the d comes after s and p, like sp3d2. D comes after s and p. Then it is a outer orbital complex. So now you can see that this forms a outer orbital complex.
Yes.
Because all d orbitals are occupied, so it will form outer orbital. Whereas, in this case, where cobalt was cyanide as a ligand, all 6 electrons were paired and these 2d orbitals were hybridized with S and 4s and 4p to give you D2sp2. So if D is coming before S and P, it is inner. If D is coming after S and P, it is outer. It's simple.
Yes.
That means the N value of D, when I write D2sp3, it is N minus 1 D2 NS NP3. Whereas when I write sp3 D2, all N values are same.
Yes.
That is the difference between inner orbital and outer. Whether I use a penultimate d orbital with the valence s and p orbital for hybridization, or I use all valence orbital for hybridization. That is the difference between inner and outer orbital complex. Is it clear?
Yes.
To all of you?
Yes.
Which d orbital I am mixing with s and p? S and p are always valence orbital, outer orbital. When I mix the inner d orbital, it is inner orbital complex. When I use outer d orbital, the valence d orbital, it is outer orbital complex. But when I said but, that it means there is some problem. For example, if you have D1, D2, D3 configurations, say titanium 3 plus is D1, vanadium 3 plus is D2, chromium 3 plus is D3. Okay? All of them are forming Ml6 octahedral complex. What will be the hybridization? I have 5d orbitals. When it is d1, I have 2 vacant d orbitals. I need only 2. Even if more than 2 are available, only 2 are required.
Yes. Yes.
So it will be all. They will always be inner orbital complex.
Yes.
Yes.
D2 will have this, D3 will have this.
Yes.
So D1 will have 4 vacant d orbitals, D2 will have 3 vacant d orbitals, and D3 will have 2 vacant d orbitals, and I require only 2 d orbitals. So of D1, D2, D3, irrespective of the nature of the ligand, will always form an inner orbital complex, and the hybridization will be D2sp3. Now you understand why I said but? Because D1, D2, D3, they never form outer orbital complex. They will always form inner orbital complex. Similarly, D7, D8, D9. Okay? D7, no orbital is available.
Yes.
Where it is high spin. What is meant by high spin? Means more number of unpaired electrons. And low spin means less number of unpaired electrons. So high spin refers to more number of unpaired electrons. Low spin refers to less number of unpaired electrons. High spin, the pairing energy is not provided. Low spin, the pairing energy is provided to pair the electrons. As a result, the number of unpaired electrons decreases. Is it clear?
Yes.
So D7, high spin will have how many unpaired electrons?
3.
Low spin will have how many unpaired electrons? Very good. So D7 low spin will be but even if it's low spin, do I have those two d orbitals available?
No, sir.
So it will always form an outer orbital complex.
Outer orbital complex.
So D7, D8, D9. And the hybridization will be sp3d2?
sp3d2.
Never d2 sp3. Because I don't have vacant 2d orbital. I can't use one from the lower, one from the higher. No. Either two lower or two higher. Simple. Is it clear that why d1, d2, d3 will be always inner orbital?
Yes.
D7, D8, D9 will always be outer orbital. Only D7 can form high spin, low spin. D8 and D9, there is no high spin, low spin. For D8 there will be 2 unpaired electrons, D9 there will be 1 unpaired electron. When the octahedral complex is concerned, for ML6. I am discussing the octahedral complex.
Yes.
Okay?
Yes.
So for octahedral complex, only D7 among D8, D7, D8, D9 can form high spin, low spin. But D8 and D9 will always form high spin. If unpaired electrons and D9, there is no question of high spin or low spin, there will be 1 unpaired electron. Because you have 5 orbitals, 9 electrons. When you have 5 orbitals, you draw 5 boxes and put 9 electrons. Will there be 1 unpaired electron or not?
Yes.
So D7, D8, D9 will be always outer orbital. And D7 can form high spin, low spin, but not D8 and D9. Which are the leftovers? The leftover is D4, D5, D6. They are the vulnerable ones. They can form inner or outer orbital complex. When they will form inner orbital complex? When the metals with strong field ligand.
Strong feeling.
Outer orbital with weak field ligand.
Yes.
How do I differentiate that the ligand is strong field or weak field? Hybridization, if D4, D5, D6, if it is weak field ligand, what will be the hybridization?
sp3.
You have 5 boxes. You have 4 electrons, 5 electrons, 6 electrons. And these ligands cannot provide you pairing anything. So what type of hybridization you will have?
sp3d2.
sp3d2.
Yes.
Okay? For D4, okay, D6, high spin, low spin. Calculate the mu as value. Give me the values immediately for D6. For high spin, for low spin, what will be the mu as value?
Low speed zero, low spin zero, and high speed four.
High spin means without pairing. Low spin means all pairing. So mu as value for high spin, what will be the value?
Root 20.
And what will be the value of here?
Zero.
So it will be paramagnetic and it will be diamagnetic.
Yes.
So you can differentiate whether you have the low spin or the high spin. If I have high spin, I will have magnetic moment. What will be the equation for D6 high spin? What will be the hybridization for D6 high spin? Just now, sp3d2.
Yes.
For low spin, what will be the hybridization? Because now I can 6 electrons I can accommodate in 3 orbitals. So I have 2 4 orbitals available. So for low spin, it will be d2 sp3. For spin, it will be sp3 d2. So by measuring magnetic moment, I can predict what is the hybridization. I can predict what is the strength of the ligand. How strong is the metal-ligand interaction?
Yes.
Whether it's a high spin or a low spin, weak field or a strong field, hybridization, whether it's D2sp3 or sp3d2. All these information will come from one measurement, that is magnetic. Similarly, for D5 high spin and D5 low spin,
Low spin 1, 2, 3. High speed 24.
D5 high spin, what will be the magnetic moment?
30.
Root 35.
Root 35.
You have 5 electron, 5 boxes, 5 unpaired electrons. So 5 electrons, group 35. What is the mu value for low spin?
3.
So you see, you can differentiate by measuring magnetic moment. 1.73 and 6 Bohr-Mann meter. So you can differentiate very easily that whether it's a high spin or a low spin, whether it's a, if it is a high spin, what will be the hybridization?
SP3D.
So there is no d orbital available. For low spin,
D2SP.
so it will be d2sp.
D2SP.
So it forms an inner orbital complex. Okay.
Yes.
So high spin for d4, d5, d6, high spin outer orbital, low spin inner orbital. Okay?
Yes.
What will be the value for d4, high spin and low spin?
High speed root 24 and 24. Root 24. SP3D2.
Root 24. Bohr magneton, you have to mention Bohr magneton. It has the, and hybridization,
SP3D2.
because you have
1 d vacant. 1 vacant.
so there is only one d orbital available, which is of no use to me. Because I require 2 orbitals. Okay. So there will be 4 unpaired electrons for high spin That means metal ligand interaction is not strong enough to provide me pairing. So it's a weak field ligand will give me high spin complex. Strong field ligand will give me low spin complex. What will be the mu(s) value for the low spin? And what is the hybridization?
Zero and D2 SP3.
0 and
D2SP3.
D2SP3. This is correct, but this is wrong. D4 is the only exception to the box. Box diagram gives a false impression that all d orbitals are equal in energy when you have a particular geometry. No. D orbitals have equal energy only in the metal in the gaseous state, not in a preferred in a particular geometry. In an octahedral, which we are discussing, in octahedral geometry, the d orbital will split into two.
X square minus y square minus y square.
I have already told you when I discussed the color.
Yes.
So, when it is low spin, that means the energy gap is large. This energy gap is large, so the electrons would occupy the lower energy orbit. Okay? Now, these three orbitals, dxy, dxj, and dyj, they are equal in energy.
Yes.
So they have equal electron affinity. Now you tell me what will be the magnetic moment. Now it is, now it is 2 root 2. So never ever say 0 for D4 low spin.
Yes.
Only for D4 low spin, this box diagram will give you wrong result. For all other configuration, it is giving right result. Only for low spin, D4, it will give a wrong. And what will be the hybridization?
D2SP3.
Because these two d orbitals are not occupied. Now I have written here dxy2 does not mean hey, they have equal energy. They have equal probability that two electrons could be here, here or here. Okay, the other will have one in it. You have 3 boxes and 4 electrons. So the one box will have 2 electrons and the other 2 will have one. Which will have? You can't say. Because they are equal in energy. So they have 1/3 probability to have both the electrons. So now you understood that why I said that you can't predict inner orbital or outer orbital. That depends upon whether you ask me sp3 d2 or d2 sp3. Now you understood that where it will be d2 sp3, where it will be sp3 d2. Where the metal ligand interaction is weak, but d1, d2, d3. It will always be inner orbital. d7, d8, d9. It will always be outer orbital. So you can't generalize that whether it will be inner or outer. Depends upon the electronic configuration of the metal. But D4 to D6, yes, they can show both outer or inner, depending on the nature of the ligand. Weak field ligand, outer, strong field ligand, inner. Is it?
Yes.
Yes, sir. Yes.
Excuse me, sir.
Now,
Sir, is it the case that a strong ligand will behave as strong ligand for complex formation with any metal, or it depends on the metal with which the ligand is reacting?
I'm going to discuss that issue just now. Have you understood what I said up to now?
Yes.
Now from octahedral, I go to coordination number 4. For ML6, coordination number is 6.
6.
What is the coordination number here?
4.
In both cases?
Yes.
Nickel in both cases is 2 by plus.
Yes.
Chloride is minus, cyanide is minus.
Yes. Yes.
Okay, both are anionic ligands. But chloride is a weak field ligand because I have told you up to iron 3. Halide was a weak field ligand.
Yes.
If it is a weak field ligand, if chloride is weak field ligand, what will be the hybridization? And what will be the mu S band?
SP3 and SP3.
With coordination number 4, I have already told you.
SP3.
Nickel 2 is D8 configuration.
Yes.
When you have D8 and the weak field ligand, there will be no d orbital available.
Yes.
For coordination number 4, you have either sp3 tetrahedral or you have dsp2 square planar.
Yes.
Now, I don't have vacant d orbital here, so it will be sp3
SP3.
root 8 Bohr magneton.
Yes.
But with strong field ligand,
DSP.
okay, so now I have not answered your question. I have just shown you that how the spin magnetic moment will change depending on the strength of the ligand. Both are coordination number 4, but one shows a tetrahedral geometry, another shows square planar geometry. If it is square planar, it has to be diamagnetic. If it is tetrahedral, it has to be paramagnetic. Okay?
Yes.
Now, now your question is answered. Nickel, palladium, platinum, all are Da. Look at your periodic table. Nickel, palladium, platinum.
Yes.
They are in the same group.
Yes.
Copper, silver, gold, they are in the same group. But silver 3 and gold 3 will be isoelectronic to palladium 2 and platinum 2.
Yes.
Silver is 4D, 9, 5S, for 4D10, 5S 1.
Yes.
So if I remove 3 electrons, do I get 4D8 configuration or not?
Yes.
So all are isoelectronic? Irrespective of the nature of the ligand, they will form always a square planar complex with coordination number 4. Now you see, in case of nickel, cyanide gave you square planar, chloride gave you tetrahedral. But platinum, whether it is KTPTCl4 or KTPTCl4, both are diamagnetic. Both are square planar. So, now you got the answer of your question or not? That as we go from the first transition to second or third, the separation increases. The ligand behaves as a strong field ligand, so the pairing of electrons takes place. As a result, the dsp2 hybridization is possible. For nickel, it was decided by the strength of the ligand. But for platinum, palladium, it is, whether it's water or halide or cyanide, all will give the same configuration, that is square planar.
Yes.
So if you have platinum class 2 with coordination number 4, close your eyes and write square planar.
Excuse me, sir. Sir, please explain this once again. Means why with platinum or palladium the nature of the ligand does not affect and we get square planar geometry.
Because I said this, the separation between these d orbitals keeps on increasing as you go down the group for the transition methods. Okay. So the square planar complex will be favored over tetrahedral.
So if the separation between these two orbitals means if it increases, then it will be difficult for weak field ligand to means pair up the electrons. Na?
There is no weak field ligand. All behaves as a strong field ligand for palladium, for all these 4. All will provide the pairing edge.
Yes.
So you don't have to worry about it. Whether it's a strong field ligand or a weak field ligand. All behaves as a strong field. There is no weak field ligand for those 4. Now there is another explanation is there. What is that explanation? Why tetrahedral? Why square planar? Why nickel could not form all square planar, whereas why platinum or palladium, they form only square planar, no tetrahedral? Why? Because if you have tetrahedral configuration, what is the angle between ligand, metal, ligand in tetrahedral geometry? What is the angle in tetrahedral geometry? What is the angle? Don't you know the angle of in tetrahedral geometry, sp3 hybridization? What is the angle in sp3 hybridization? Is it not? Don't you know that? That in a sp3 hybridization?
Yes.
Yes.
tetrahedral, the angle of separation is 109.5 degrees. Well, what is the angle of separation here?
90
90 degrees. Okay. So where the ligand will be closer to each other? In a square planar. So there are two things to be considered. One is steric crowding, and second is metal ligand interaction. Strength of metal ligand interaction. When the metal ligand interaction is weak, the steric crowding will determine the geometry. Chloride was a weak field ligand, so steric crowding was dominating feature. So the tetrahedral geometry was favored because square planar will give me lot of steric crowding. Tetrahedral will place the ligands away from each other to a larger distance. Where the interaction is very strong, K2NiCN4, the metal cyanide is a strong field ligand. So the metal ligand interaction, when it is strong, it ignores the steric crowding and gives me square planar geometry. That is for nickel. For palladium platinum, since the central atom size is large, although the ligands are 90 degrees, but they are quite separated. And since they are quite separated, the steric crowding does not play a role. So it always gives me a steric square planar complex and never tetrahedral complex.
Yes.
One is all ligands behave as a strong field ligand, and strong field ligand will prefer a square planar geometry over tetrahedral geometry. Because then the metal ligand interaction becomes stronger in a square planar rather than tetrahedral.
Yes.
Okay, now, so for you, what will be the for cobalt 3 complex where water is a ligand and ammonia is a ligand?
Yes.
What will be the hybridization?
SP.